So let's take a look at the ring systems for the Jovian planets. When you see a picture of Saturn, of course, the rings around Saturn are always part of it. And when we look at this picture, they almost look like they're solid, but it turns out that they're actually made up of a ton of very tiny individual particles, some ranging from size of small rocks to large boulders. They are all orbiting around Saturn. They actually are following Kepler's third law, so the closer they are to the center of Saturn, the smaller the radius are and the faster they're going. And so they're all orbiting individually. It isn't a solid piece of material. They're very thin if you look from top to bottom, and in fact, sometimes during Saturn's orbit around the Sun, it actually presents to us in a way so that we're actually looking at the very edge of the rings, so that we actually can barely even see them. But this is actually a good opportunity for astronomers to find other small satellites or moons that are orbiting around Saturn that have been sort of blocked from our view from Saturn's rings. This is what Saturn looks like if we view it from the Earth. This is actually a view of the rings from a spacecraft, and now you can start to see that they're the structure and how they're actually really pretty in this picture. But you can see that they're banded nature of them, because everything in the same distance away from Saturn, of course, is going to be orbiting at the same rate, because they do orbit according to Kepler's laws. So Kepler's laws actually will be obeyed for anything that's orbiting under the influence of gravity. It doesn't just have to be the planets orbiting around the Sun, it can also be moons and other objects orbiting around a central planet. This is a nice way to sort of visualize what's actually in those rings, and you see like all these just pieces of rock and stuff or ices that are orbiting around, and because there's so much of it, it just forms the rings. There are some gaps within the rings. This picture right here shows you a really small gap, and the reason for that is because there's this little moon within the ring. So it's big enough that it's considered a moon, and because of its gravitational influence, it actually sort of pushes other ring particles out from that orbit, and so it kind of maintains its own orbit there, but it's cleared out everything else. There are also sometimes what we call shepherd moons. You see this very thin ring right here, and there's a little moon here and a moon here as well, and we call them shepherd moons because in a sense their gravitational influence kind of shepherds the ring particles into a very thin line and keeps them like that. So it's lots of interesting gravitational stuff going on in these ring systems. There's this gap. There's a gap in the rings, and you even see it in the Earth-based picture, and it's called the Cassini gap, and it's actually because it's a location that's in an orbital resonance with one of the larger moons of Saturn. And what that means, a resonance is when some force is applied in a very regular manner. Like when you push a kid on a swing, you know that you have to push sort of with a certain cadence to make the child swing higher and higher. And that's sort of an example of resonance. When you have these gaps, what's happening is, of course, all the particles that would be in that gap would have the same orbital period. But their orbital period is related in a very simple way to an orbital period of a moon that's further away. Say, every time they orbit twice, the moon orbits once, or something like that. And what that means is if their orbital periods are related in a very simple way, those ring particles will pass the moon in a very periodical, predictable way. And every time they do pass the moon pulls on it with their gravity, and what gradually happens is those particles get pulled out of that orbit, and you end up with a gap. So it's another interesting example of gravity. Like I said, there's lots of stuff going on in these ring systems. So let's take a look at the other ring systems. I mean, we actually had no idea that there were other ring systems until, I'll talk about it in a minute, we found the ring systems around Uranus. And then when Galileo got out to Jupiter, astronomers thought, well, maybe all the Jovian planets have ring systems. And so they looked and they actually found that there is a thin ring around Jupiter. We see here's a picture of all the 4 Jovian planets, and notice that they all have rings around them. They all have a ring system. They're different from each other, but they all have them. This is a picture of Uranus. Remember, Uranus pretty much rotates on its side. This might have been caused by a large impact early in its formation. And so you see that the ring system still goes around its equator. It just is tilted along with the planet. And Uranus is kind of important because it was the second Jovian planet that we found a ring system around, and we found it quite by accident. There's this phenomena that astronomers use to study atmospheres of planets and other stars, and it's called stellar occultation. And what it is, it's when a star is being blocked by another object that passes in front of it. And so they were doing this study with Uranus was passing in front of a star, and they were studying how the light was affected. You know, if the light goes through Uranus's atmosphere, you can learn a little bit about what the atmosphere is made of. So that was sort of the purpose. But what they found, quite by accident, is they found the rings around Uranus. So here is, in this graph, you see is how bright the starlight is and over time. And what they found was that there were these periodic dips in the brightness of the starlight that came before the planet itself passed in front of the star. And then once the planet had continued on and passed the star completely, the dips in the starlight happened again. And basically the conclusion was that these dips were caused by the rings that were around the planet, which were actually blocking the starlight from our view. And that's how we found the ring system of Uranus, which actually led to the conclusion and verification that all the Jovian planets did have ring systems. So we might wonder, why do they have rings? So there's something called the Roche tidal zone, and this again has to do with gravity. It's a region where we find the ring systems in the Jovian planets. So in a sense, there's a special location, a distance from each planet, which is called the Roche Limit. And if you're closer to the planet than that limit, then you're in the Roche zone. And if you're further away, then you're outside of it. When you're in the Roche zone, the tidal forces, remember tidal forces are when the gravitational forces across an object vary, which is why they were called tidal forces, because it's what causes the tide. So that the part of the object that's closer to the gravitational pull feels a stronger pull than the far side, which feels a weaker pull. And so there's sort of this difference in the forces from across the object. When you're within the Roche zone, the tidal forces from the planet are stronger than the gravitational forces that hold the object together. So essentially what happens is when objects go within the Roche limit of a planet, they get torn apart. And so here's a little picture sort of showing that. Here we have a large satellite, and you see as it starts coming to the Roche limit, it's being sort of, the tidal forces are deforming it because it's being pulled so that it stretches out, and once it gets within the Roche limit, it breaks apart and it, forms the particles that can make up the ring system. You might be noticing why, you might be thinking, oh, but wait a minute, she showed me a picture where there were little satellites within the ring system. How can that be true? Remember that the characteristic said that the gravitational tidal forces were stronger than the gravitational forces that were holding the object together. If the object's being held together by other forces, like electrostatic forces, those are actually strong enough to withstand the gravitational tidal forces. And so some satellites that are being held together by a force other than gravity can exist within the ring system. So basically the idea is that we believe that the rings have formed when a lot of the debris that existed after the planet formation got pulled into the Roche limit of the Jovian planets and got torn apart and then started to orbit in a regular manner. And so part of the reason that these planets are able to have these big ring systems has to do with the fact that they are very large, and so that their Roche limits are a significant distance away from the planet itself. But it's really kind of cool. And that's it.